When you watch a biological dog run, you are seeing the result of millions of years of evolutionary trial and error. The Unitree GO1 achieves a nearly identical fluid motion, but engineers built its entire architecture in a few short years. Getting a machine to move like an animal requires solving what roboticists call the balance crisis. Walking isn't actually a state of stability. It is a continuous, highly controlled state of falling forward, where the body constantly catches itself just before it hits the ground. This diagram shows the core physics problem, the inverted pendulum. A mass on a pivot naturally wants to tip over. Applied to a 12-kilogram machine moving at 17 kilometers per hour, gravity is constantly pulling its center of mass toward the Earth. The margins for keeping that mass upright are punishing. If a single real-time calculation adjusting a leg's position is off by a single millimeter or delayed by a single millisecond, the robot's center of mass slips past its base of support, and the machine violently crashes to the floor. Because the real world is filled with unpredictable terrain, gravel, and sudden obstacles, engineers could not rely on a hard-coded walking script. Instead, they had to invent a machine that continuously recalculates its own stability. To replicate the fluid adjustments of an animal, the robot's physical skeleton requires 12 degrees of freedom. That means each of its 4 legs has 3 distinct joints for the hip, thigh, and calf, giving it the physical geometry to pivot and catch itself in any direction. Older robotic designs place the motor, the gearbox, and the processing controller in different locations. Connecting them required wiring, and wires create a few microseconds of latency, enough delay to cause a fall. This diagram shows how engineers solved that bottleneck by sliding the motor, planetary gearbox, and motherboard together into a single 3-in-1 joint. Eliminating wiring removes signal delay, generating 23.7 Newton-meters of torque locally, allowing microsecond adjustments with enough force for a standing backflip. But generating raw mechanical power doesn't keep a robot upright if the machine is entirely blind to the terrain it's stepping on. To read its environment, the GO1 uses a network of 10 fisheye cameras that capture a complete 360-degree spherical view of the world. Because cameras fail in pitch darkness or when facing glass doors, they are paired with a network of ultrasonic sensors that map proximity using sound waves. The visual data is then combined with physical proprioception. 4 sensors installed in the bottom of each foot measure resistance upon impact, instantly detecting if the ground below is solid concrete, soft grass, or slippery mud. These advanced joints and sensor arrays don't actually generate the walking motion themselves. They are strictly data-gathering instruments, continuously feeding the physical variables of the outside world into a central math equation. Taking in thousands of sensory data points and calculating the necessary motor torque for 12 separate joints takes immense processing power. Forcing one single computer chip to handle 3D visual mapping and microsecond physical balance at the same time would overload the processor and trigger a fatal system crash. This flowchart illustrates a dual brain architecture. The incoming data splits. The lower tier, a digital spinal cord using proportional, integral, derivative controllers, executes instant balance reflexes. Meanwhile, the upper tier's NVIDIA Jetson chips act as the thinking brain, processing video to generate a 3D environment map. The hardware is receiving the data accurately, and the processors are running without crashing. The central question remains, how does the digital brain actually calculate the exact motor commands required to keep the robot from falling over? Engineers didn't write the instructions. Instead, they built a 100% accurate 3D physics simulation of the real world and used a technique called reinforcement learning. In this generated video, an AI model is given a single rule: do not fall. It attempts to move, fails, and crashes to the floor. After every single collapse, the algorithm tweaks its neural weights, adjusting how it calculates torque and angle, until the motor outputs effectively offset the gravitational pull. Once the algorithm learns to navigate the virtual physics, engineers execute a sim-to-real transfer. They take the mathematically optimized digital brain from the simulation and download it directly into the physical aluminum hardware. The physical machine standing in front of you is entirely hollow of instinct. It is simply a physical vessel built to execute the specific mathematical weights determined during its simulation training. The robotic dog does not know what a step is. It has absolutely no concept of what it means to be running. It is simply a physical calculator. It takes millions of terrain data points from its feet, combines them with visual inputs from its cameras, and optimizes its neural network equation 1,000 times every single second. That relentless computational speed yields highly practical, real-world results. Using its intelligent sensor system, the robot actively fuses its camera data with a wireless transmitter in its owner's pocket. This allows it to dynamically predict the human's path and walk safely beside them, rather than following behind like a standard tracking drone. Applying that level of environmental mapping to an agile frame makes it effective for mapping hazardous environments, executing autonomous search and rescue operations in collapsed buildings, and serving as a highly interactive digital companion. This technology moves beyond simple pre-programmed scripts. We have reached a point where a computer manages physical gravity through real-time, high-speed calculation. Subscribe to Zero Logic for more deep tech breakdowns.